Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 9th, 2025, about 2 days ago. The main idea is a single system that completes videos from arbitrary spatial patches at any timestamp, delivering fine-grained control with zero new parameters and outperforming past conditioning methods. The paper is titled VideoCanvas, Unified Video Completion from Arbitrary Spatio-Temporal Patches via In-Context Conditioning. And as we'll see later, the results are really impressive. It tackles temporal ambiguity in causal video encoders, using spatial zero padding and a temporal RoPE interpolation trick, plus a new benchmark to validate broad, unified control. Also, the author shared a GitHub repo. You will find a clear README describing the unified video completion tasks, a teaser video under assets, and notes about the forthcoming VideoCanvas bench. The core implementation is marked as coming soon, so code, models, and usage examples are expected to be added shortly. Alright, Figure 1 shows the central promise. A single model completes videos from whatever patches or frames you place in space and time. Arbitrary spatio-temporal video completion means the user pins down a few pixels across moments, and the system fills the rest consistently. The top block illustrates scattered patches that become coherent scenes. The middle block demonstrates full image prompts at chosen times. The bottom block displays Inpainting, Outpainting, camera control, long extensions, and zero-shot scene transitions. Alright, Figure 2 explains the core obstacle and the fix for pixel frame-aware control. Causal video encoders pack several frames into one latent code, which makes specific timestamps hard to target. The left panel depicts our hybrid idea. Zero padding handles spatial placement, while Temporal RoPE Interpolation assigns fractional time positions, like 1/4, to align the correct frames. The right panel contrasts methods, showing that latent replacement and channel concatenation falter, while in-context conditioning with RoPE alignment works reliably. Figure 3 shows the full pipeline for turning scattered patches into a temporally aligned video. The left block presents conditional patches that are zero-padded for placement, then independently encoded by a frozen video autoencoder, so spatial control does not tangle with time. The center column runs in context conditioning, which mixes conditional and noisy tokens, while Temporal RoPE Interpolation assigns fractional time positions like 10.25. The right panel depicts generated frames that respect the specified timestamps and preserve content inside the red masks. So, Figure 3 outlined the pipeline. Table 1 reports how alignment choices affect single-frame image to video. The RoPE interpolation version leads motion with a dynamic degree near 40, which signals stronger and smoother movement. It also tops imaging quality at about 72, suggesting cleaner, more appealing frames. Latent space conditioning peaks in PSNR at about 25, but that score comes with very low motion because the dynamics collapse. So, Table 2 compares conditioning paradigms across all task groups on VideoCanvas bench. It shows that latent replacement scores the highest PSNR, but collapses motion, because dynamic degree is about 21 for any P to V. Channel concatenation adds movement yet trails on fidelity and on human preference. In contrast, in-context conditioning achieves the best balance, with the highest dynamic degree and roughly 60% overall preference, while keeping strong FVD and PSNR. Wrapping up, 2 takeaways stand out. The method unifies many video tasks into one interface by dropping patches on a canvas, and rotary position encoding interpolation resolves the temporal ambiguity in causal video encoders, giving precise control without adding parameters. The broader impact is practical, creative video editing that stays efficient on frozen models. That is it for the AI Research Roundup. I am Alex. Thanks for listening.